Alrighty, lads and ladies, welcome back. I appreciate you guys being a little bit patient with me. I finished updating all of our videos. So everything from 9/24 through today is now either available or currently uploading. So I know I spoke with Sarah a little bit yesterday about getting those videos updated. And while yesterday was a crazy day, I did not manage to get around to it then. It has been done now. So if you need to go back and review any of the old lectures, they're there, or will be there. Should be done uploading at least by the time we finish our class today. Let's get to it because today is another fun day. Show you real quick what I'm talking about. Here we go. Yeah, everything is updated. So we got videos for everything from 9 to, I think 24 was missing and 10.4 was missing, maybe 10.1 was missing too. All that stuff's up now. But that's not what we're talking about today. Today we're talking about, this isn't what we're talking about today, this calculus. Today, we are going to start talking about something new, namely related rates. Let me just make sure, I'm pretty sure that's where we're at, but lately my brain is absolute mush. So we can quadruple check. Pretty sure we're at related rates now. The other thing is your exams. I am working to get them done. I ran into an issue with my MAC2311.0H1 classes. Some of the kids that took the test at the testing center, even there under the supervision of the lovely people there, managed to cheat a little bit. So I'm neck deep in that quagmire of trying to figure out who cheated and how and file the appropriate paperwork. So that's slowing the process down a little bit, but I'll be grinding on your guys' exams a little later today, and hopefully they'll be in by the end of the day today, like midnight. So we have finished talking about log derivatives. Yeah, it's time for related rates. This is good stuff. Oh, okay. Oh, is this Friday the homecoming game? Goodness. All right. So William, I appreciate you bringing that to my attention. That is an important thing. I was counting on doing stuff in my other classes on Friday too. It might be. I've got 10.1 as homecoming, but that's not correct, is it? No. Well, how did I mess that up? I've been using an earlier version here. Technically in the 2021, 2022. Yeah, let's see what we have here. October 6th, 7th. Yeah. Damn. All right, so we are going to be closed for Friday. That does mean we're not going to have class. I'm sorry about that. That's so disappointing. It kills me that Santa Fe closes for US homecoming. Some other place has a football game, so we have to close. Given that you are busy this afternoon and that the college is closed on Friday, so we're not allowed to do any official college business on Friday, we will have to find something else. Because certainly my schedule doesn't need to change for homecoming beyond obeying Santa Fe's rules. I would be happy to meet with you on Friday, William, at the normal time, at the normal office hour time. Are you available then? Alrighty, let's do that then. So I'll just go to my normal office hour in Zoom at 1 p.m. on Friday, and you can follow that same link from Canvas, and we'll chat then. And since the college is officially closed on that day, probably it'll be a very slow office hour. So we should have the whole hour to ourselves to kind of plan things out. All right, so that's all the bookkeepy stuff. Let's get moving. This is MAC2311 section OH1, which means this is Calc 1 honors. And the date today is the 6th of October. Today, we're going to talk about related rates, which is section 3.9. So for a lot of Calc 1 students, related rates is like one of two sections that they hate. Because it involves like all the things that math students despise, right? It involves word problems, right? All the related rate stuff is word problems. It involves calculus, implicit differentiation, use of different variables, right? We're not going to be using the variable x most of the time, or if we are, it's maybe going to be a dependent variable rather than an independent variable. All of those things that we kind of, when we encounter them one at a time, usually try to skirt around, are going to pile up here. So the related rates is one of those areas that's a little on the tricky side. I'm going to do my best to kind of outline a procedure that is more or less effective on all of these problems. And you're going to want to practice these a little extra hard. I can tell you now, the other section that's like this in Calc 1 is section 5.1. When we start talking about areas under curves, we're going to be using the sigma summation notation. That's the other one you need to watch out for. But for exam 2, this is the guy, right? 3.9 is the one that people don't like. So what are related rates? If you look out your window, you're going to see a bunch of shit moving, right? You're going to see, tree branches waving in the wind. You're going to see cars rolling down the road. You're going to see water droplets falling and forming puddles that grow. Anytime you have a physical system where things are moving and connected to one another, you have a related rates problem. So for example, as a car rolls down the road, there are two rates of change that are connected to each other in an intimate way. The ones that come to mind for me immediately are the RPM of the wheels turning, right? The speed of revolution of the wheels and the velocity of the car, right? If the wheels turn faster, the car goes faster. If the wheels turn slower, the car goes slower. Those are two rates of change, they're speeds, right? And they are related to one another in the sense that if one changes, the other changes. There's a direct, clear connection between those two rates of change. That's what we mean by related rates. The other example that comes to mind right away is as rain falls and collects in a puddle, the puddle grows, right? So the rain is falling down, you're adding volume to that puddle, and the puddle's area, the surface area, the top of that puddle will grow. So there's another related rate. The volume is changing. It's a rate of change for the volume. And the radius of that circular puddle is increasing. That's another rate of change. So how do we want to introduce this? What we'll be looking at here are, let's say, many systems connect two or more rates of change. Through geometry, right? Like in the example with the car, there's the geometry of the wheel and the geometry of the car's trajectory. The geometry can usually be expressed through algebra or trigonometry. I'll just say trig. To then find the relationship between the rates of change we can differentiate implicitly that geometric relationship. So you can go from an algebra relationship relating a radius to a volume and differentiate on both sides of that equation to get some rate of change for the radius and some rate of change for the volume connected through another equation. Related rates is all about that. So you look at your dynamical system, the thing that is changing. You use the geometry of that system to relate two variables or more to each other. Then you differentiate through that equation with respect usually to a third variable, which most of the time will be t, representing time. That will give you a new equation where you've got some derivative over here, maybe some other algebra stuff, equals some derivative over here with maybe some other algebra stuff. And then you can plug stuff into that final equation with the derivatives and the algebra to find how one derivative changes with the other derivative. I think that's about as clear of a high-level explanation as I can give without looking at a specific example. So let me grab for you a few classic examples. We'll start simple here. The area of a circle is related to its radius by the equation A equals pi r squared. All right, the area is equal to pi times the square of the radius. If the radius is changing over time, so like r is secretly r of t, a function of time, then so is the area, right? If you change the radius, the area will change. Let's find the relationship between two derivatives, dr dt, which is the rate of change of the radius, and dA dt, which would be the rate of change for the area. Okay, so how do we do this? If you're going to study physics or engineering or anything where you apply calculus to the real world, this is your bread and butter. I begin with the equation A equals pi times r squared. And I apply the appropriate differential operator to both sides. I want to find, I'm assuming that the radius is changing over time. So my independent variable, the thing I'm trying to find the rate of change with respect to, is t, which means the operator I should apply to both sides is d dt. So on the left-hand side, I would have d dt of A, and on the right-hand side, I would have d dt of pi r squared. And the idea here, pi, of course, is a constant. This does not change over time. Pi is the same to me now as it was to someone 5,000 years ago. But the radius is changing and the area is changing. So d dt of A looks nice algebraically, and it is true, is dA dt. On the right-hand side, I can pop out the pi, and then I would have, because it's a constant, d dt of r squared. And the trick here is to remember that I'm differentiating implicitly, right? We're differentiating not with respect to r. If this was ddr, not the game, if this was the differential operator ddr, then the derivative ddr of r squared would be 2r. But remember, r is secretly a function of time. Yeah, the game or the type of computer memory, right? Double data rate memory. I'm sure DDR's got other meanings. But silliness aside, r is a function of time. I'm not differentiating with respect to r, I'm differentiating with respect to that function of time. So you have to pretend like this is a little function in here and use the chain rule. In other words, you're differentiating implicitly. So what is the derivative ddt of r squared?
2r multiple
r prime.
dr dt.
You guys both gave different answers and you're both correct. Now my only comment here would be to Sarah, I'm not going to use the prime notation here. I love the prime notation, don't get me wrong. I'm a big fan. I think it's nicer, it involves less writing. This like gnarly ass, I'm not flicking you off, this gnarly ass callus on my finger doesn't get worse when I use the prime notation. But because there are a total of 3 variables here, if I use the prime notation, it's unclear which variable I'm differentiating with respect to. See, if there's only 2 variables, x and y, and we always understand y is the dependent variable and x is the independent variable, then the prime notation is great because we know it always means ddx, right? We know it always, y prime is always dy dx. But here, would r prime be dr dt, dr dr, or dr dA? There's 3 possible interpretations. And the prime doesn't tell us, but the Leibniz notation does. So while you both gave the correct answer, the one I would write down would be the one that Yiping gave, 2r times dr dt. Now I don't have a problem with you using, there is a notation here. Let me share this with you. So for fans of the prime notation, one can write r dot. This is a very common notation in physics and engineering for dr dt. In the same way that the prime always means derivative with respect to x or derivative with respect to whatever the independent variable is, the dot always means derivative with respect to time. So I could have written here instead, a dot equals pi times 2r times r dot. This is, I know it looks a little silly, but it is actually a very common notation. I'm not going to use it much because there's already so much notation in this class. But if you like that notation, I'm fine with you using it. And double prime, double dot, triple prime, triple dot works just the same. The question.
I have a question. A here is a function I can understand, but why do we put the r is a function here too?
Well, so that was my assumption, is that the radius is changing over time. So I imagine this circle, right? And for whatever reason, the radius is changing. As a consequence of that, A is also changing. So yes, A and R are both functions of time. I didn't write it explicitly here, but yeah, A would also be a function of time. So you can picture this, right? If I have a circle, imagine right here, a circle, as the radius changes, so does the area. If one of them is a function of time, then the other one is automatically a function of time. And that's what I mean when I say that they're connected through geometry. Because of the geometry, if one changes, the other changes. So if one is a function of time, the other is also a function of time. Does that feel a little, does it answer the question?
Still cannot really understand because before the x, we always think derivative x is 1, but here the derivative r become a function.
True. So in other words here, both A and R are what are called dependent variables. And the independent variable is time, t. So even though it doesn't show up anywhere in the equation, both of these, A and R, are dependent variables. The variable that we're differentiating with respect to, right? I'm differentiating with respect to the variable t, doesn't show up anywhere in the original equation. And that's okay. So in answer to Daniel Anyping's last question, yes, Sarah answered it in the chat. That's perfect. Both A and R behave the same way that Y behaves. So normally Y is the dependent variable and X is the independent variable. So here, both A and R behave the same way that Y behaves in implicit differentiation. Yep, and what Sarah said in chat is exactly correct. A is really A of t, it's a function of time. R is really R of t, it's also a function of time. So the independent variable is t, and both A and R do the same shit that Y does when you differentiate. It's a little bit weird, right? It takes a little getting used to. But this is how the physical world works, right? When you turn on your faucet and start filling up a cup of water, the volume increases, and as the volume increases, the height increases. So both the volume of water in the cup and the height of the meniscus are functions of time. So this it's just the nature of the real world that dynamic systems evolve over time. So time is almost always the independent variable here. It's very rare that something other than time is your independent variable. And anything else that is able to change is a dependent variable, dependent upon time. All right, so we have solved this problem. We were asked to find the relationship between dr dt and dA dt. And the answer is that the rate of change of the area, how fast is the area growing? It's 2 pi r times the rate of change of the radius. So I could go a little further here. No, we'll separate examples. So we'll keep these things compartmentalized. Do we feel okay with how we arrive at this expression? I like what you guys are asking. I like what you guys are saying. I'm just curious, is there anything else on your mind? All right. Now, in order to make like good exam problems, questions that you can ask in homeworks and tests, I would be asking you for one of these rates of change at a specific moment. Like, how fast is the area growing at the moment when the radius is 5? Something like that. I would have to give you 2 extra bits of information. I would have to give you the rate of change for the radius and a specific value for the radius r, and then and only then could you compute a number for dA dt. let's try one. Let's try a nice simple one. All right. I made a snowball. I mean, obviously not in October in Florida, but I made a spherical snowball. And it's melting. And maybe I have a little graduated cylinder underneath where my snowball is sitting. And I measure how quickly the water is dripping off the snowball. So I know the volume of the snowball.
4/3 pi r cubed.
Yep, we'll get there. But let me go ahead and state the rest of the problem. So I know the volume of the snowball is decreasing at the rate of, let's say, 2 centimeters cubed per minute. So I'm losing 2 cubic centimeters off this snowball every minute, right? That's a volume over a time. And I'd like to ask, how fast is the radius shrinking at the moment when the radius is 5 centimeters. All right, so I've got my snowball sitting in like a colander. I'm measuring how much water is falling off of it every minute. And then I want to look at the specific moment in time when my snowball has a radius of 5 centimeters, big snowball. I want to know at that moment, how fast is the radius shrinking? And the place we begin is exactly what Yiping said. We're going to begin with the relationship between the volume of a sphere and the radius of the sphere. It's always nice to draw a picture. So here's a sphere of radius r, and you know, water is dripping off this thing. So it's shrinking. I know that the volume of that sphere is 4/3 times pi r cubed. So if at any moment in time I knew the radius, I could find the volume, right? But that's not what I'm asking. I'm asking how fast is the radius shrinking at the moment when the radius is 5 centimeters. So what I need to do is relate the radius rate of change, which is dr dt. So I want, this is the procedure I always run through for these. Figure out what it is you're looking for. I want, how fast is the radius shrinking? So I want dr dt, or r dot, if you prefer that notation, at the moment when r is equal to 5. See, dr dt may not be constant. Dr dt may itself be changing. So I need to specify the moment I'm looking. What do I know? Well, in addition to this volume relation, V equals 4/3 pi r cubed, Does the problem tell me anything else, specifically about rates of change? Can anybody tell me another rate of change that is given to me by this problem?
The volume's changing like by 2 centimeters per minute.
Very good. In other words, dV dt, the rate of change for the volume, and I want to be careful here, it's decreasing at 2 centimeters cubed per minute. So I would say this is -2 cm cubed per minute. Negative rate of change means decreasing, right? Positive rate of change means increasing. All right, so now I've got a picture. I've got my geometry formula. I know what I'm looking for, and I know what I have in my pocket. Now we will differentiate both sides of this relationship implicitly with respect to the third variable, time. So I'm going to apply the differential operator d dt to both sides. Well, I'll pop out the 4/3 and the pi. d dt of v is dv dt. And on the right-hand side, I have 4/3 pi times 3r squared times dr dt. And it's at this stage where we stop. We ask, what do I know? What do I want? I know that for all time, no matter when you look, dv dt is -2. And here I can cancel the 3's, and I get 4 pi r squared times dr dt. So this is true always. Now what I want is dr dt, the rate of change for the radius, at the moment when r is 5, I should say 5 centimeters, I'm sorry, 5 centimeters. 5 what? 5 miles? No, 5 centimeters.
So r squared is equal to 25.
Very good. So what I get now, when r is equal to 5 centimeters, we have -2 is equal to 4 pi times 5 squared dr dt. As a mathematician, I'm not super picky about your units, but you do need to be a little bit careful. So here, every unit of length is in centimeters, and every unit of time is in minutes. So I don't need to be super paranoid about my units. But if your problem gives you different units for a length or different units for time, you'll need to convert one into the other. All right, this is equivalent to saying -2 is equal to 4 pi times 25, which is 100 pi, times dr dt. So then I divide both sides by 100 pi, and I get -1 over 50 pi is dr dt. This is what I wanted. So the radius, first off, I get that the radius is shrinking because this is a negative rate of change. And it's shrinking by 1 over 50 pi centimeters per minute. Quite quickly, right? I'm sorry, no, quite slowly, I should say, I'm sorry. 50 pi is quite large, so it's reciprocal. This is like 150, right? So like 1 over 150 centimeters per minute. And that would be our answer. Okay, and you see connections to physics, right? Very, very important.
So if the questions ask for the shrinking by how many, I just plug the number in it. I don't need to put the negative sign in it.
That's correct. If I just asked what is dr dt, then you would say -1/50 pi. If I ask you how fast is it shrinking, the shrinking is the negative. So you can just say 1/50 pi. Other questions or comments here?
Quick question regarding, we started with a unit centimeters cubed over minutes and ended with a unit centimeters over a minute. What happens with the units? Unit conversion is not 100% my strong point. So what happened before it got to the end?
Yeah, that's fine. Let's look at this carefully. So let me come back to this relation. And we'll look carefully at the units. So we're not actually doing any unit conversion, but the dimensional analysis works out well. Volume is being measured in centimeters cubed, and time is being measured in minutes. So this is really -2 cm cubed per minute. The 4 pi is unitless. And then the radius here is being measured in centimeters. And dr dt, r is being measured in centimeters. So this is dr dt being measured in centimeters per minute. So if you look very, very carefully, the left-hand side has units centimeters cubed per minute. The right-hand side over here, you have centimeters squared times something with units centimeters divided by something with units minutes. So the units on the right side do match the units on the left side. All right. Both the right and left-hand side here have units cm cubed per minute. They are both rates of change for volumes. If you go and solve this for dr dt, what you would find is that you're going to get centimeters per minute out. Let's see, how can I write this nicely? So the units, how could I write this nicely? It's a little tricky. So I guess the cleanest way to think of it is that dr dt itself should have units centimeters per minute. So if I leave this over here and I divide all of this stuff over, when I plug in r equals 5, right? Because I've already got the units here. This would be -2 cm cubed per minute equals 4 pi times 25 centimeters squared, 25 times cm squared times dr dt cm per minute. When I divide over by the 4 pi blah, 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 you get -1/50 pi. When I divide by the centimeters squared, so I'll write out the dimensional analysis here. This is cm cubed over minutes times 1/cm equals dr dt. And the right-hand side, I claim, would still have units cm per minute. And you can see here, if you cancel one of these cm's, then this would become a square. And you really do get -1/50 pi. The 1 centimeter remains up here. The minute remains down here equals dr dt. So the units do work out just fine.
Cool, I see it. Thank you.
Very good. Now the trick, if you are ever getting nervous about your units, rather than like solving and checking, do you have the right units? Just go back to your original thing and ask, do the units match on both sides? So here I have cm cubed over minute. This piece has units cm squared. This piece has units cm over minutes. So if you multiply cm squared times cm, you get cm cubed and the minutes downstairs. So that is called dimensional analysis, and it's a great tool in physics. If you're wondering, does this make sense? Check and see if the left and right-hand sides really have the same units. Sometimes you can even come up with cool stuff just like this. This is how you calculate the speed of light in physics too. You look at Maxwell's equations, and then just do the dimensional analysis, and you realize that the piece that's missing has the units, meters per second. All right, let's try another. A man and woman leave from the same place. The man walks north at 2 miles per hour, and the woman walks west at 1 mile per hour. How fast is the distance between them changing 1 hour later? So here I have kind of even less notation to start with, right? Because the geometry doesn't, I don't have like an A and an R. We have to pick variables. But if we begin by drawing a picture, start labeling stuff, then we'll get there. So here's my picture. Let's say they both start here at the origin. The man is going north, so he's going up the y-axis. So I'll just call his position y. So here's the man. And I'll say he's at the point 0, y. He's going north. And the woman is going west. And I'll say she's at the point x, 0. The distance between them, the straight line distance between them is this. Okay. Ooh, actually, little d is a bad thing to use for distance here because we're going to be using Leibniz notation for derivatives. Let me call it L instead. All right. So here, x, y, and L all change with time. X, which is the position of the woman. Y, which is the position of the man. And L all change with time. I want dl dt. And I want it 1 hour later. I'll just say that. By later, I mean after they start walking. What do I know? What rates of change do I know?
We have their velocities.
Good. Yeah. So how do I connect that to a derivative?
L square is equal to x square plus y square.
That's good. That's the geometry formula we're going to use. Yep. I'll write it as x squared plus, oh shit. I'll write it as x squared plus y squared equals L squared. That's coming from the fact that this is a right triangle. And that's completely correct. We are going to use that. But
X is equal to dx dt multiple 1.
let's hold off on the differentiation. Before that, let's just figure out from this, like this 2 miles per hour or this 1 mile per hour. Oh, sorry, you can't see the woman's speed there. 1 mile per hour. What are these in terms of derivatives?
So dy dt is equal to 2 miles per hour, and then dx dt is 1 mile per hour.
Perfect. I know that dy dt is the speed that the man is walking north, right? If he's at the point 0, y, and he's walking at 2 miles per hour, then y is increasing 2 miles every hour. So dy dt is +2, and the units here are miles over hours. I'll put units in the bracket like this, the MIT notation. And dx dt, this lady's walking over here at 1 mile per hour. Okay, now we have everything that we need. Now we can differentiate through this implicitly with respect to time. What you'll see here is that we're going to end up needing some more information, but it will be information that we can find. So if I apply the operator ddt to both sides, ddt of x squared plus y squared equals ddt of L, the left-hand side will become 2x times dx dt plus 2y dy dt. And the right-hand side is dl dt. So the right-hand side is the thing I want, but I don't know everything on the left-hand side. Let's plug in what we do know. Dx dt is 1.
I think that d dt L is d dt L square.
Thank you. Yeah, this should be L squared. I'm so sorry. So this is 2L dl dt. I'm sorry, I forgot to write the square here. Yeah. You're 100% right. And that will change my derivative. All right. So we've got 2x dx dt. That's 2x times 1 mile per hour plus 2y dy dt. Dy dt is 2 miles per hour. And over here, I don't know any of this stuff. This is 2L dl dt. If it's okay with you, in the next step, I'm not going to write the units. So what we have here is 2x plus 4y equals 2L dl dt. We can make our lives a little simpler by dividing both sides by 2, which means x plus 2y is equal to L times dl dt. And this is all well and good, but I don't know x, y, or L. In fact, they all change. We know that those are not constant. But I know that I'm after dl dt 1 hour after these people leave. So now what we have to do is come off to the side and say, okay, 1 hour after they leave, what is x? What is y? And what is L?
X is 1 mile per hour multiple 1 hour is equal to 1.
Very good. Yeah, so the woman walking to the west is walking at 1 mile per hour. So 1 hour later, she will have gone 1 mile. Y, the dude, he's walking north at 2 miles per hour. So after 1 hour, he will have gone 2 miles. What about L?
We could use Pythagorean theorem to find it.
Very good.
Yeah.
And usually what I'll say is that oftentimes you need to redraw the picture. So you'll draw one picture in general, right? Like the purple picture up here is good for all time. And then I'm going to draw a separate picture down here at the specific moment I'm interested in. So the dude is up here 2 miles north of where they set off. The lady is over here 1 mile west of where they set off. So 1 hour later, L can be computed by the Pythagorean theorem, because again, right triangle. So L would be this, I'll write it like this, L squared would be 1 squared plus 2 squared. In other words, L is the square root of 5 at that moment. Technically, when you take the square root, you get a plus and a minus, but L is a distance, right? It's a length. So it's definitely not the negative square root of 5, it's the positive square root of 5. So you can plug that back in up here. L would then be the square root of 5, and this is also being measured in miles. So this stuff we can now plug in over here. X is 1, y is 2, so 2y is 4. L is the square root of 5, and dl dt is dl dt. So 1 plus 4 is 5. Which means L is 5 over the square root of 5. Sorry, dl dt is 5 over the square root of 5. And this is in miles per hour. So the distance between them is increasing at 5 over root 5 miles per hour at that moment. Good stuff, right? Questions on this one? Five over root 5 we can simplify, right? That's just the square root of 5. But yeah. Yeah, it is neat, right? This is Newtonian physics. It's the good stuff. This is where your industrial revolution comes from. All right, all the relationships, when you think about a complicated machine, you know, you've got things spinning and reciprocating. The amount of reciprocal energy you get from a spinning cam can be calculated this way. All sorts of cool things can be calculated this way. I think we might have time for just one more. So let me see if there's something cool in here we can poke at for these last few seconds. That's literally the problem I just did. This one's okay. Man walks along a straight path, 4 feet per second. Searchlight located on the ground, 20 feet from the path. Kept focus on the man. What rate is the searchlight rotating? And the man is 15 feet from the point closest on the path to the searchlight. All right, let's take a look at that. So we'll get some triggering. So maybe he's running from the cops. Who knows? Searchlight is kept focused on the man. As he walks. We need to look at the geometry of the problem, right? So they say he's walking at 4 feet per second. And the searchlight is 20 feet away from the path. We want to know 15 path. How fast is the searchlight rotating? Path. How fast is the light rotating when the man is 15 feet past the point on the path closest to the light? So what I'm going to do is give a top-down view of this situation. I'm going to draw a picture where we're looking straight down from above. Here's my path. Here's my light. I know that this light is located 20 feet off the path, right? So this distance right here is 20 feet. And I know my dude is walking like this at 4 feet per second. What I want to know is how fast is this light rotating? So I'm going to label that angle in there as theta. And you'll notice I can construct a little right triangle. The catch is you have to come up with some variables again, right? You have to label things in a way that is useful. So what I would do, I would call this distance right here, the distance the man has walked past the line where the light is closest, where the light would have been looking straight at him. I'll call that X. What do I want and what do I know?
I have a question. How fast the light rotating when the man is 15 feet? It means X is equal to 15.
Right. Yep. So what I want is something when X is 15. What is the something I'm after? When we say how fast the light is rotating, what derivative would represent the rate of change for the rotation? Sarah, I'll flash that back up after we finish this. So let's, I want to keep this cohesive.
I think we want d data over dt.
Exactly. How fast is that light rotating? That's how fast is that angle changing. And I want this at the moment when X is 15 feet, right? What do I know?
We know dx dt is equal to 4.
Very good. Dx dt is 4, and the units here are feet per second. Now, again, if you leave your units off, I won't take off points, but you do have to be careful and make sure that all the lengths are being measured in the same units. So if I said he's walking at 2 miles per hour instead of 4 feet per second, you would have to convert miles per hour into feet per second. Either that or you'd have to convert all the other distances to miles. But here we're lucky, everything is in the same units. What is the relationship between X and theta?
They have a trigonometric relationship.
Definitely some trig, yep, because I've got a right triangle in here and I'm trying to relate one of the angles to one of the side lengths. We have a choice of trig functions to use, don't we? So
We have two sides. We have an adjacent and an opposite. We could use tangent.
Exactly. Yep. And Talia also got that in the chat. That's very good. So because the two sides that I know are the opposite and the adjacent, our good choices here would be either tangent or cotangent. I'm going to go with tangent. You could also use cotangent. Cotangent is the adjacent over the opposite. So that would put my X downstairs, which is not as nice as having the X upstairs. I would rather differentiate X than 1 over X. So we know that the tangent of theta is equal to the opposite over the adjacent, which is X over 20. And I'll leave my units off in this to make the calculations less scary. And turns out both sides here are unitless. X is measured in feet, 20 is a feet, and tangent theta is definitely unitless. It's just a number. So if I differentiate both sides with respect to t, I'll have d dt of tan theta equals d dt of, I'm going to write this as 1/20th times x. And I'm doing that to emphasize that the 20 is a constant. So there's no need for a quotient rule here. The bottom isn't a function of time, only the top is. So we might as well write x over 20 as 1/20th times x. That way, instead of messing around with some quotient rule stuff, I can just pop this out. On the left-hand side, I get by the chain.
Secant square.
Very good. Yep, secant squared theta times
D theta dt.
Perfect. And on the right-hand side, I'll pop out that 1/20th, and I just have d dt of x, which is dx dt. And now we plug in what we can. So I know dx dt is 4. We get secant squared theta times d theta dt is equal to 1/20th times 4, which is 1/5. And then one more thing I would do, I'd say since secant theta is 1 over cosine theta, I would take this and say d theta dt is 1/5 cos squared theta. But there's still an issue, namely, I don't know what theta is. So this is true for all time, right? Regardless of the moment we're looking, this is always true. But at the moment, when x is 15 feet, let's redraw the picture. So I will need to find the cosine of theta here. In order to find the cosine of theta, I need to solve for this hypotenuse. So I'll just label that as h, and we'll solve for it. I know that h squared is 20 squared plus 15 squared, which is 400 plus, what is 15 squared? I'm not sure off the top of my head. 225? So h is the square root. Oh, this is nice, of 625, which I think is a perfect square, right? Isn't that 25 squared? Yeah.
Yeah, I think so.
It is. All right. 5 cubed. All right. So h here would be 25. So that means cos theta. So at the moment, when x is 15 feet, we have d theta dt is equal to 1/5 times the square of cos theta. And cos theta is the adjacent over the hypotenuse, right? So that's 20 over 25, all squared. And we can clean this up if we want. That's 1/5 times 400 over 625. And 400 is definitely divisible by 5. What is that? 60? Yeah, I think so. Oh wait, no. What is 400 divided by 5? 80, right? Yeah. And we could clean it up further, but I'll just leave it at this. Well, no, let's see. So 10, 2, definitely both. No. Then 5 is the only common factor. What is 80 divided by 5? My arithmetic, not good.
16.
All right. So this would be Oh, did I lose my, no, I didn't. Okay, so this is 16 over and 625 by 5. I'll do what, 5 cubed? 125, yeah, good. All right. All right, and now that's a power of 2 over a power of 5. That won't simplify. That is theta is increasing, right? As this thing, come back up here. Theta is increasing because this angle is getting larger. Okay, real quick, what are the units? At 16 over 125, what? Yeah, Daniel, there is not going to be class Friday. We're closed for homecoming, as much as that sucks. What are the units for d theta dt?
Second?
Something per second. What was the something?
Feet?
Not feet, radians. So remember theta, when you're looking at trig functions, theta is measured in radians. So this would be radians per second. Alrighty, that's where I'll end it for today. So this is related rates. It's not that hard, but it does involve some implicit differentiation and a little bit of geometry. And the implicit differentiation is almost always done with respect to a third or fourth variable time, something totally independent of X, Y, or whatever. So practice these. You do have problems up in the homework set for you to work on. And if you get stuck on anything, you can come see me in office hours. I'm going to continue working on your exams. I'll get them done as soon as I can, hopefully this evening. If you need anything else from me, you guys know how to reach me. You can Canvas message, email, Discord, any of that stuff is fine. That is it. Take care, guys.